In the name of God. In this presentation, we will present an article entitled Joint ADC-less Analog Demodulator and Decoder for Extended Binary 844 Hamming Channel Code. New generation of wireless communication systems, 5th generation and 5G beyond, encounter with tremendous growth in the number of connected devices. Higher data rates and less latency is needed. The capacity of the expected wireless communications is anticipated to grow 1,000 times every 10 years. Frequency band below 10 GHz, which is commonly exploited by approximately entire telecommunication systems, reaching its saturation point in near future. For this reason, migration to millimeter wave spectrum is being assumed as the next vital step for the upcoming wireless systems. Millimeter wave is the band of spectrum between 30 to 300 GHz. One of the main challenges in this area is regarding to the ultra excessive speed and power dissipation which is arising from digital signal processing. Recently, to solve these challenges, an analog QAM demodulator as an approach to mitigate the high power consumption problem of digital implementations is proposed. As you can see, instead of analog to digital converter, it uses the illustrated circuit. MREQAM is a spectrally efficient modulation scheme which eliminates the need for extra bandwidth expansion to achieve higher data rates. Dual ring MRE star QAM scheme has the signal points arranged on two amplitude levels R1 and R2 such that each level consists of half of M points which are distributed at a constant phase difference. In general case, star MQAM with N rings is called NR star MQAM. The signal point of an NR star QAM constellation can be expressed as the equation shown, where RZ is the Z's ring radius. For NR star MQAM constellations, amplitude decision regions DAI can be calculated as the equation expressed. Now we will discuss more about linear block codes. In general, the channel encoder block received information sequence U and transformed them into code word V, where G is the generating matrix. At the receiver side, the received vector Y is the vector sum of the transmitted code word over a noisy channel and error vector which can be expressed as Y equal V plus E. Because the receiver does not know either E or V are received, the syndrome S of R is computed as the equation expressed, where H is called the parity check matrix. The general process of the decoder for a linear block code is shown in this slide. From the received signal, the syndrome is calculated, and after using the error pattern detection circuit, the corrected bits are calculated. Now, in this section, we will describe the proposed method. In this slide, we can see the typical wireless communication system and the proposed scheme. In the proposed ADC-less architecture, we subjoin two decoding and demodulation blocks, which are shown in this slide. Consider the following generating matrix for 844 Hamming channel code. This matrix is designed to place 2 bits of message in the first 4 bits of the code word and another 2 bits of the message in the last 4 bits. By multiplying the messages in the generating matrix, the code words are generated according to shown 844 Hamming channel table. The output of code words is modulated by 4-ring star 16 QAM modulation. In this case, the code words are selected 4 to 4. It means that at first U0, U1, P0, P1 are modulated, and then U2, U3, P2, P3 will be modulated. If we look at the output of the code words, we have only 8 of the 16 possible signal points. 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 0, 0. Figure shows the structure of the transmitted signals. Functional diagrams of the proposed 4-ring star 16 QAM with extended binary 844 Hamming channel code is depicted in this figure. The proposed amplitude adaptive scheme consists of the absolute value circuit, envelope detector, phase detector, and some logic gates. The absolute value circuit is utilized to compare the estimated amplitude threshold with the amplitude of the received signal. To realize this, pulse conversion from input sine waves is required, which is done using amplitude tracking and using op-amp. In the proposed 4-ring star 16 QAM scheme, 3 amplitude thresholds D1, D2, and D3 are needed to be obtained. At first, D2 is calculated adaptively and also directly from the threshold estimation circuits. After calculating D2, 2 other amplitudes thresholds, D1 and D3, are obtained by comparing RAT with D2. This process is done by a comparator circuit C. Another important part of the suggested 4-ring star 16 QAM with extended 844 Hamming channel code is a phase detector. Phase detector circuit consists of an analog multiplier, a low-pass filter, and also 2 op-amps. Via X, I and J and D, I, R, J are comparator circuits that are designed for phase and amplitude thresholds respectively. Now in this section, we will describe the message bit recovery in the proposed method. In proposed circuit, 2 message bits are identified from the received signal at each stage. First, U0 and U1 bits are detected, and in the next step, U2 and U3 bits are detected from the next received signal. In the proposed circuit, it should be noted that error correction is performed only in the first bit of the message, which is related to the threshold amplitude estimation. The reason for this is that there is a large angular distance between giant symbols in the four-ring star MQAM constellation, which reduces the probability of error occurring in the second bits of the message and the first parity bit. The simulation result confirmed this claim. Now we explain the process of error correction in the proposed circuit. Consider U0, U1, P0, P1 are transmitted. When the phase of the received signal is between alpha 1 and alpha 2, or is between alpha 3 and alpha 4, and U0x or P1 equal 1, then there must be an error in U0 or P1. In this case, when the amplitude of the received signal is between D2 and R2, it means that the first bit has been received with an error. In a similar way, when the phase of the received signal is between alpha 2 and alpha 3, or is between alpha 4 and alpha 1, and U0x or P1 equals 0, then there must be an error in U0 or P1. In this case, when the amplitude of the received signal is between R1 and D2, it means that the first bit has been received with an error. In this section, simulation results are reported. This table compares the proposed method with related works. As shown, this is the first paper that has been worked on joint ADC-less demodulator and decoder. This figure shows the bit error rate performance of four-ring star 16QAM joint ADC-less analog demodulator and decoder with extended 844 Hamming channel code. In this simulation, we assume that the amplitude threshold includes EAT equal 10% distribution with R0 equal 1, R1 equal 2, R2 equal 3, and R3 equal 4. This simulation result shows that by correcting the error bit related to the amplitude threshold estimation, the system performance is improved. This figure illustrates the comparison of the bit error rate performance of four-ring star 16QAM with extended 844 Hamming and different phase errors. In this simulation, we assume that the amplitude threshold includes EAT equal 10% distribution error, and also different phase errors are assumed. For example, 5, 10, and 15, which means that phase of the received signal has an error of 5, 10, or 15 degrees in comparison with transmitted one. The result of this figure show that the construction performance well against phase mismatch and phase errors. This reason in the four-ring star 16QAM instruction because the angular distance between giant symbols is large enough. In this presentation, we propose a joint ADC-less analog demodulator decoder for n-ring star MQAM constellations. In this study, extended binary 844 Hamming channel code has been used. In the proposed ADC-less architecture, we subjoin two decoding and demodulation blocks. We extract the message bits directly from the received analog signal without separating the in-phase and quadrature components of the signal. So receiver IQ imbalance problem is solved in this scheme. With the assumption that carrier synchronization is already achieved, we eliminate the need for ultra-high-speed ADC. This suggested scheme can be considered as alternative to power-hungry digital implementations. Thank you for your attention.